Hello, this is chapter 23 of the second edition of the Top Hat textbook. In this one, we're going to be talking about the acidity of alpha hydrogens. And what we mean by that is the acidity of CH bonds immediately adjacent to C double bond O's. Okay, and so if you look at the pKa of different CH bonds, if you have just a regular alkane, it's going to be like 44. But remember we had talked a couple chapters ago where if it's on a terminal alkyne where you've got a CH here, you've got a you have a massive drop in pKa. This becomes incredibly acidic. If you instead put this next to a C double bond O, you drop further in the pKa. So for this one, it's not just slightly less, it's 10,000 times more acidic than the terminal alkyne, because remember each unit of pKa is a factor of 10. Okay? And so we can do that, okay, because because if you remove this with a base, you can get resonance stabilization for here, right? This lone pair can come down here to make a new double bond. That carbon can't have 4 bonds, or it can't have 5 bonds, so it needs to push those electrons up, and you can have the electrons up here on the electronegative oxygen. Okay? And so you're able to put have that oxygen bear the charge, right? It's really electronegative, so it's fine. And so this is much more likely to occur. Okay. The reason why it's called alpha carbons is because if you're having if you have, say, this, if this is your reference carbon, okay, then the alpha carbon would be the one immediately adjacent to it. This one here would be the beta. This would be alpha beta. Was it gamma? So gamma and delta and whatnot. So this would also be an alpha over here, something like that. And so going out. So that's why it's called an alpha hydrogen, because it's one carbon away. And apparently we really like our Greek and Latin terms in our in science. So notice that if you were to try to remove the beta hydrogen here, right, you'd be too far away from the C double bond O to be able to get this resonance structure, right? The CH2 from the alpha carbon would be in the way. That's why it's just the ones that are adjacent to the C double bond O's. Those are acidic. Okay, and when you get to when you get to biochemistry, in order to be able to, even something as simple as glycolysis, there's one of the first steps in glycolysis is to move a C double bond O over, and it's a trivial sort of reaction because you're going from one type of ketone to another. Going from an aldehyde to a ketone. But in doing so, what you're doing is you're moving which CH bond becomes acidic. Okay, glycolysis couldn't happen in our present form if you didn't move that C double bond O, because by making that adjacent carbon their CH bond acidic, then we can snap the two the sugar in half into 2 3-carbon pieces. Okay, and then we can take both of those to do the second half of the glycolytic pathway. But this is the reason why this works is because this this alpha hydrogen, right, this CH bond that's immediately adjacent to this C double bond O, is acidic because it can get this resonance stabilization. Okay. So you can form what's called the enol or the enol or the keto form. Okay. So with that, so the enol, right? So this is from alkene, right? And this is from the alcohol, right? So you can actually go back and forth between these two. They're not resonance structures, right? Because they are you're moving that hydrogen. Okay, but it can go between these two. Okay, again, it's not a resonance structure because notice how this goes from, right, that hydrogen moves. from here to there. Now, for the most part, for most C double bond O's, okay, most aldehydes and ketone, it's going to want to be in that keto form. Okay, acetaldehyde, acetone, right? Much less than 1% is going to be in this form. Same thing goes with something like cyclohexanone. You're only looking at 99% of it still going to be in this form. Okay. The difference comes is when you have the beta diketone, right? Because remember, if this is a reference, right? This is alpha, this is beta, right? So that's why it's a beta diketone. What can happen is it actually likes to be in this form more. Okay? For a couple of, and so what it allows it to do is allows you to get this really strong hydrogen bond here, right? Because remember that you got a partial negative, partial positive, partial negative, okay? In this really nice cyclic structure. And so if you can form that very strong hydrogen bond, that helps to stabilize it. So in the beta diketone form, it's actually mostly in this form here. But that we'll talk about the implication for that in a minute. Now, one of the things that we can do with this is just like with any other acidic hydrogen, we can remove it with a base, right? So lithium LDA is just lithium diisopropylamine. Okay, it's a really strong base. It works very similarly to sodium hydride or sodium amide here. Okay. This this is going to, right, it's a negative charge, right? It's going to grab this, put those there, and then we can use these to do just a simple SN2 reaction. Okay, displace the iodine, and here we go. Those is here. Same thing goes here, right? We can remove one of these hydrogens. It doesn't. In this case, it doesn't matter which one you take. Right? This one of you can take one of these acidic hydrogens. You can take this as a nucleophile, nucleophilic carbon, and displace leaving group. Right? Remember, this is just a simple SN2 reaction, and voila! Now you've made a new carbon-carbon bond. So it's a nice way of doing it. But the other thing we can do is we can come in here. I think I got the mechanism. Is we can actually put halides on these alpha carbons. Okay, so you can either do it under acidic or basic conditions. We're mostly going to focus on the basic, under basic conditions. But under base, you can come in here, right? You're going to be removing that hydrogen, collapse down, to make your you're going to make your enolate here, and that can come in and attack, keep this away. Right, so this is no different than when we were adding, when we were adding alkenes, right? So halogens to alkenes, right? The alkene would come in and attack one end of the Br2, right? Displace the other one, and so we're going to be making this new halide, carbon halide bond. So it's a nice way of putting in a halide right next to a C double bond O. Okay. And so if you have something like this, okay, well, this is a really strong base, so you have to look at the most acidic hydrogen. Okay. So for that, it ends up being right here. So this LDA is going to grab that there, and so you're going to end up with that. And then that can come in and attack this good leaving group here. And so what you would end up with is this. Right? If you want to put in your dots, right? Plus Br minus. Okay. So for here we have a base. Right? We're looking for the most acidic hydrogen, and that turns out to be just right here. But again, that's going to grab that, get this away. Right? And then that's going to attack the I. There, so displace that, and so what you're going to end up with is an iodine where that acidic CH was. plus I minus. Now for the aldol reactions, what's going to be happening is you're going to be reacting two aldehydes or a ketone, but we're just going to be doing this as a nucleophilic attack. Okay, and so what we can do is we're going to be making a new carbon-carbon bond, right, sacrificing an aldehyde or ketone. And so if you're looking at something like this, we put in some hydroxide. Right, that's going to grab that. You're going to be left with that, right, plus water. Now that can come in and react with another molecule of, in this case, acetaldehyde. It's going to attack here, kick that up, because but it can't collapse down, because if it tried to, you would either be kicking away a carbon group, either this one, or a hydrogen. So it's not going to get, so that's not going to form, and so it ends up getting protonated as from the during the workup. So you end up making this. It'll be kind of exaggerated so that you can see it, but like that. So you're going to make a new carbon-carbon bond between the carbon that you removed and the carbon of the C double bond O. So that ends up being this bond here that forms. Now this is the aldol addition product. If instead you come in here and you heat it, okay, what's going to happen is you're going to lose a molecule of water, and again, between the carbon where the acidic hydrogen in it and where that C double bond O, this new bond here, you're going to lose a water molecule and form a carbon-carbon double bond. And the reason why this can happen is, one, you usually heat it, so you drive off the water, but also notice how you're putting these in conjugation. Okay. So under basic conditions, you're going to do the aldol reaction. Okay. This can then come back and get the water, which reforms your base. Again, this hydrogen here is going to be acidic because, again, it's next to the C double bond O. This can collapse down to make the double bond, kick away the O minus, and again, you're going to be getting your OH minus back. Okay, you can also do this an aldol type reaction with esters. Okay, but again, you're going to be, but this in this way, you're going to be able to the mechanism. Right. You're going to be right, again, you're going to be removing the hydrogen here, so it collapses there, to make this. Right. Now that is going to come in, attack here, right, up, down, kick away. And so what you're going to end up with is this. The hydrogen's still there. R. And then here, like that. Okay, so it's just an aldol reaction, except you're working with esters. So again, this can come in So for here, if you're looking for the aldol addition reaction, right? So this one doesn't have any alpha hydrogens on it, so it can't. You can't remove this. Okay, move a hydrogen here, but there is one here. Okay, so this is going to come in here, grab that to form. And then that's going to attack there. Kick this up because we're right. You would have to break a carbon-carbon bond or a carbon-hydrogen. Right. It ends up being the O-, which ends up getting protonated into the workup, and so what we end up getting is this. Right, for a Claisen, right, we're going to do the exact same thing where we're going to be removing these, right, we're going to be removing the hydrogen, moving that there. That's going to come here, right, up, down, kick away. And so what you would end up with is one, two, three, four. There you go. Plus. Now, being next to one C double bond O makes that CH bond acidic. Being next to two makes it incredibly so. Okay, so with that, so it's not just that it's twice as acidic. It's like 10 billion, right? Because go from 20 to 10, right? It's 10 to the 10th fold more acidic. Okay, so the so it's really easy to take these off, and the reason for this is the fact that you can get the positive, this negative charge onto a bunch of different three different atoms, two of which are incredibly electronegative. Right? So we can get it here or here with the resonance structure. So that makes removing this not a big deal for the molecule, so it happens readily. Okay. Now, one of the things that can happen is, again, we can come in here and we can make a, we can add some base, right, to make carbanion. We can then come in and do the, just do a nice SN2 reaction, right, so to here, kick away our halide, okay. But we can do this again, because remember, there's another hydrogen here. Okay, so again, this can come in, grab this, there, right, and then we can come in and do this again. Oops. Ah. Right, and then this can come in and do it again. Right, so we can do this more than one time, right? Because we have more than one acidic hydrogen here, right? Because there's these two, we can take advantage of both of these. Okay, so if we wanted to run through this, okay, so we added the sodium methoxide, right? So that's going to come in, grab that, put that, put those electrons up onto there, and so you would end up with okay, and then we can dump in, say, ethyl bromide. going to come in, kick that away, and so what you would end up with is this. But we have another acidic hydrogen here, right? So we can go through the cycle again. Right? If we put in some more sodium ethoxide, put that there. Right? Now let's put in, say, methyl bromide. So now that's going to come and displace that, and you would end up with this product. No problem. So this is what you would end up with. So you're replacing these two acidic hydrogens with new carbon groups. Now, one of the things that happens with this, oh yeah, so it looks like that. So if we want to, okay, we've exhausted the sort of what we can do with this. But what we can do is we can remove the ester portion of these groups, okay? And so it's always the same way. We have to put in sodium hydroxide, right? And that just comes in here. Right, up, down, kick away, and so you'd be left with the carboxylic acid. But because you put in a lot of sodium hydroxide, you end up with the carboxylate. Okay, because then more hydroxide comes in and deprotonates it. If, however, you then acidify it and then heat it up, you get this rearrangement here, and what ends up happening is this gets lost as CO2, and you end up removing what used to be the ester group. And so this is where that carboxylic acid was. Okay. And so if you did this same reaction, right, came in here, put this group on, you got to here and you said, okay, we have what we need, let's turn this into let's get rid of this. You put in sodium hydroxide and turn it into here, put in acid and heat, and then this gets removed, and so you end up with these with this chain here. This chain here, let me get this in a different color. This chain here is this chain here. And this is where the, no wait, hold on. This is where the original CO2 was. It was hanging off of here. So if we came back and came back to our original molecule, right, which looked like this. Oops. We went through a cycle of sodium hydroxide and then acid and then heat. What you would end up getting is you would get this whole thing removed, and so it would look like this. If you rewrote it, then it would look like that. Okay. And it's just the ester side. Okay. Now we can take this one step further, as instead of having an ester on one side and a methyl ketone on the other, we can do this where there's esters on both sides, but otherwise it works exactly the same. Okay? So you come in here and you add the, right, you get, this comes in, right, grabs this, grabs the hydrogen, and then comes in and displaces this, that carbanion displaces the bromine, kicks that away, you'd end up with this. Now, if you then put, in this case, potassium hydroxide, that doesn't matter, right? You're actually going to make both of these, turn both of these into the carboxylate. Okay. Then we added our 4-carbon piece here. when we do the acid and heat, one of those goes away, and it doesn't matter which one you do. Okay, so acid and heat. Oop. Acid and heat. One of these is going to go away. So let's get rid of that one. Doesn't matter which one. But just one of them. And so you end up with, in this case, your hexanoic acid. Okay. But otherwise it works exactly the same. Okay. But again, you can come in and you can put two different groups on here. Okay, because you've got two different acidic hydrogens. Okay. But when you come in here and do the hydroxide step, you're going to take away the ester for both of these, convert both of these into carboxylic acids, and then when you heat it, only one of them is going to go away. So you're going to end up with this. Doesn't matter which one. So if we wanted to use this to design a synthesis, what we're going to want to do is we're going to want to start with something like this, and this is how I would, do this, to say, like, okay, we're going to be starting with this molecule, and how do we get to here? So the first thing we're going to want to do is we're going to want to see where the group, what carbons here end up here. Okay, and so if we come in, right, if this, here's our C double bond O, and then here, that's going to be this. Okay. But then this carbon here, right, is going to be this carbon here. Right? Because remember, we're going to remove one of those, one of the ester groups. We're going to decarboxylate it to remove it. Okay, so that carbon group goes away, but that means that these two carbon groups are from the original malonate. Okay, and so what that means is we're going to have this carbon piece here that we're going to add. Right, so we need to add this carbon piece, but then we also need to add this carbon piece here, like that. We're going to be connecting them together. Okay? But this carbon here is originally from the malonate. So let's run through the synthesis, because it's going to work the exact same way for all of them. Right? You just need to know which carbon groups to add. So we're going to add sodium methoxide. It's going to attach here. And again, you don't have to show the mechanism, but sometimes it's easier to see. Right? And then usually put on the larger one first. So let's put on this 1, 2, 3, 4, 5, 6 carbon piece. Right? So we're going to have 2, 4, 6 bromine there. So that's going to attack there. Kick that away. And so we're going to have this. That. Now let's go through the cycle again. Okay, so we're going to add, again, some sodium methoxide. That's going to attack there. Now we're going to add our 2 carbon piece here. Right, that's going to attack there. Kick that away. And so we're going to have our 2 carbon piece and our 6 carbon piece. Right, so when we hit it with sodium hydroxide, right, both of these are going to be coming off. Okay? So you're going to end up with this. I guess technically it would be that. And when we hit it with acid and heat, right? Let's say this one goes away, and you're left with this. But that's how they all work. You had to get the carbon bits on, and then hit it with sodium hydroxide, and then acid and heat, and there you go. Good luck.